All right, welcome back. We are Game 2005. That's Game Physics in the fall 2021 semester, and it is week 4, part 1 of our broadcast. Part 2 could be from Joss if he's going to produce videos for you guys for the tutorials. So welcome back. Again, we're sitting at week 4. This week, we're talking about the laws of motion. And assignment 1, just things that are due. Assignment 1 is due this week, Friday at midnight. That's when the first assignment's due. It's a group assignment. Assignment 2 has been released. I'll go over assignment 2 details today in brief. And that is due 2 weeks from now, week 6. That's Friday, October the 15th, I believe, at midnight. So again, that's kind of just after the Thanksgiving long weekend. So it's going to be due that week. And then following that, we're going to have a midterm test that's going to cover the theory as an example that's happening for the first half of the semester. All right. So again, it'll allow you to go through your the stuff that we're covering through your brain, a couple of times. But before we start anything else, I want to talk about this. Today is the National Day for Truth and Reconciliation. And one thing we want to talk about, we want to do this land acknowledgement today, which is George Brown College, located on the traditional territory of the Mississaugas of the Credit First Nation and other Indigenous peoples who have lived here over time. We are grateful to share the land as treaty people who learn, work, and live in the community with each other. And guys, I encourage you guys to participate in activities for national truth and reconciliation, which is happening today. I was hoping that it would be more of a holiday, but I think that's something that we just didn't get from our government. Hopefully one day we'll have a chance to, to have a day, an actual civic holiday where we can, kind of take the time to share and understand stuff that's happened to the Indigenous peoples across Canada that have been hard done by, especially from a colonial perspective over, the better part of a century and a bit. All right, so lots of struggle and oppression. One thing that I regret is that I don't have an orange shirt today. That's something that I couldn't manage to do. I've been, it's not really an excuse, but it is what it is. But I think it's something that we have to continue to evolve and learn and to represent and to support the things that are happening. Again, these things that we're talking about, they're not enough. We have to take action. But I think this is at least a step maybe in the right direction. All right, let's move on and talk about the stuff that we're here today, which is it's all about the laws of motion today in section 4. Right. So I know some of you have been working on your assignment 1. Hopefully you've been working on it over the last couple of weeks and you're still haven't started. That would be a bad outcome. If you're trying to start your assignment number 1 today and it's due on Friday, you're going to be hard pressed to get it done. Remember that there are 2 parts of all the assignments that we're sharing with you. The first part is a theoretical piece. And the second part is actually a technical piece where you kind of take your physics problem that we've given you and translate it into code. And that can take a while. The reason why I've allowed partners to work on this thing this semester, or multiple people, is to give a chance to lessen your load and have a chance to work with somebody else to get things done. Because I think we all recognize, Alex and myself and Joss, that this is not your only course. There's other things that you're doing. So to try and give you a chance to work with other people. Sometimes, though, I have to be honest, and working with other people presents a bit of overhead, right? So what ends up happening is that, you're working with somebody else, but you're in a team environment. This is not your first time you're working within a team, but it can present issues because you have to wait for somebody to, to do their part after you've done your part and so on. And that can be challenging as well if they're not doing what they're supposed to do. So on that, let's talk about assignment 2, which I've just released today. Assignment 2 is all around projectile motion, circular motion, and free body diagrams and Newton's laws. It's due week 6, so that's Friday, October 15th, 2021 at midnight. It's worth, again, 10% of your final grade. It's marked out of 100 points. Again, please complete all question sections of the assignment with your group members. And the best way to complete the assignment is to complete as much of the work as possible as your own, and then get together with your group members to compare what you have and share ideas, submitting the best assignment possible. And I mean this for definitely the first part, the physics problem. The second part, you may have to work in tandem with your group members, because you don't want completely different projects and then all of a sudden saying, okay, we'll take Tom's project because his is the best, or Nick's project because his is the best, or Andre's project because his is the best. We don't want those kind of things. We want more or less for you guys to do this, the physics problem on your own, then come together and say, okay, this is what I got. What were your results? What did you find? So here's the physics problem. Consider a metal loot crate at the top of a frictionless ramp. If the mass of the loot crate is 12.8 kilograms, the ramp has a rise of 3 meters and a run of 4 meters. Then compute the following: the free body diagram, the net force and acceleration, and then consider the loot crate as it leaves the ramp and moves onto a flat surface. So draw this out, flat surface, and now has some friction. Compute the free body diagram for this situation. And if the coefficient of kinetic friction is 0.42, for example, steel on steel, calculate the new net force and acceleration. And that is your question for C. D, if we assume that the force of friction is constant after this point, how long will it take for the loot crate to stop moving? At what distance in meters will the loot crate stop? And include a short document or report that includes diagram that illustrates your problem and your solution. Ensure that you include appropriate labels and show your work. By the way, guys, this is almost the exact same format that I have for your first assignment. Please do not forget this short diagram, this short document. If you don't submit a report, you'll lose marks, 10 marks here, out of 100. It's huge as an example. And you've got to be able to show your stuff. I mean, I can't, in effect, if anything, if you don't submit this, how the heck am I going to get this? Unless you, I don't know, take snapshots of something that's handwritten or something weird. But what I'm looking for is a document that puts everything together. Yes, please. Physics simulations. This is part 2. Part 2 is how do you make this into code? So you will use C++ and the STL framework, the assignment framework provided, to create a scene which simulates the motion of the particle in the problem of part 1, like we did in the first assignment. Your application should include a start scene with labels that show team members' names. Your play scene should include appropriate assets for the physics simulation. You should include a background image or tile map. Choose an appropriate scale for your scene. So how many pixels per meter for your physics simulation. Move the asset that represents the particle in the scene according to the problem described above, and let the user activate the scene with a button or other control. I recommend using IMGUI, which is kind of part of the framework, and use appropriate label objects in your scene to show key statistics, which may include, but are not limited to, mass, position, velocity, acceleration, force, etc. You may use IMGUI for this, as it has been included with your template. Allow the user to change the variables, example, the width and the height of the ramp, the mass of the loot crate, the coefficient of kinetic friction, etc. And then update your display accordingly when they make those changes. So actually you can kind of do a little demonstration. Part 3 is your video demo, which is required just like it was for assignment 1. Please don't forget your video demo, as your assignments for both you and your partners will not be accepted for your video demo. Okay, so that's important. Lewis, what do you mean that's not an option for you? Pencil and paper is not an option for you. Yes, okay. Version control. Again, version control is required. And the breakdown of marks is roughly like this: 30 marks for your physics problem, 20 marks for your physics simulation user interface, 35 marks for your simulation functionality, 5 marks for version control, and 10 marks for your video presentation. But note, your project will not be accepted without your video demo, period, the end. All right, so please make sure that you hand in your video, you submit your video. This is for not just for assignment 2, but also for the upcoming assignment 1, which is due Friday at midnight. Guys, I've had several requests for extensions. The answer is no for most of you, unless you have a medical problem or a reason why you need an extension. That's there has to be a super good reason for it. The answer is going to be no for you. You have the due date, which is Friday, and you lose 20% for each day that you're late. I will accept late submissions as an example, but the submissions are going to be late after Friday. So make sure you submit timely and plan to submit. That means tomorrow at midnight. If you're just starting today, I mean, if there's not a medical reason or something really, there's a really good reason why you're doing that, then the answer is, well, you're going to submit late and you're going to lose marks. Okay, so that's how it's going to be. All right, so that from submitting your work perspective for assignment 2, and this is kind of the same for assignment 1, a Microsoft Word or PDF document. It could also be a Google Docs document as well. That's okay. I don't mind. I can accept that as well. Include the name and student ID of each member of your at the top of your document. A link to your working GitHub repository for your simulation. A zip archive of your project upload to Blackboard. Please remove any garbage files. And a link to your video demonstration. If you can't link it, let's say through YouTube, you can't use YouTube, you're in a country that doesn't support YouTube, I will accept things like Google Drive. You have your video on Google Drive. This is also for assignment 1. Or it could be on Dropbox or on OneDrive or somewhere else where I can click it and make it work. It doesn't have to be with YouTube, but it's important that you get this this kind of stuff done. All right, late submissions, 20% deducted for each day late. And one thing I'd also want to hone in on is be careful of the code that you use. If it's not your code for assignment 1 or assignment 2, and you've borrowed code from somewhere else, there's got to be a really good reason for it. You better cite it. And if you're unsure about the code that you're using, as an example, then in your mind you should ask me if you can use the code, right? Or ask Joss. Myself or Joss can answer that question. But the idea is, if you're unsure and you're using someone's code to try and solve one of your problems, cite it. All right. If it's more than 10% of your code base, I probably won't accept it if it's somebody else's code. And by no means are you allowed to use anyone else's code outside of your group members, right? So if you actually go to someone else's code, like another classmate, and you get their code and your code matches their code on GitHub, bad things will happen to both teams. So please don't do that. I've had that kind of submission in the past, and both teams are very, very unhappy at the end. All right. So that's something that we don't want. Make sure the code is your own as much as possible. All right. Kim says, if I've done the math on paper, can I include photos of that as the document, or should I retype? Please retype, Kim. I need to be able to see your document. I've accepted scanned copies before, and that's been a bit of a disaster. And I mean that as in, like, some people took pictures with their phone or something like that, and I can't read it. If it's not legible to me, then I can't give you marks for it. Okay, that's bottom line. If I can't open your documents, if I can't open your project, if I can't open your video, even if it exists, you're going to get 0, guys. I can't. There are 50 of you in the course or more. And there's only one of me when it comes to marking this kind of stuff. And I need you guys to help me out by doing the stuff and submitting everything appropriately. Patrick says, if we are in a group, does only one person need to submit? Absolutely. Actually, the only way you can submit for assignment 1 or assignment 2 is if you're in a group. You cannot submit as an individual. You won't even be able to submit to see the project online if you're not in a group. So as on that, for assignment 1 and 2, if you look at groups, by the way, I've also created a little shortcut, assignment groups, up on Blackboard. If you go to assignment groups, you're going to see that there are several assignment groups. So assignment group A1 groups are only for A1. And what I've done for you guys, and this has positive and negative side effects, is I've created a separate assignment group, set of assignment groups for group 2. Let's say you're really unhappy with your partner from assignment group 1. Well, guess what? Now you have a chance to, be with somebody else for assignment group 2 or on your own. All right. I've made 45 groups. If you need more, let me know. But no group, no submission. You can't submit without a group. Even if you're a group of 1, you need to join a group. So please, for assignment 1, if you haven't done that yet, you need to do that ASAP. And for assignment 2, I would plan to join a group as soon as possible as well. One thing that you can't do is you can't remove yourself from a group. So if you're in a group and you need to be removed, you have to let me know, or else that person is going to get credit. Perhaps someone joined you randomly, and I have situations like that. They've joined you randomly, you don't know who they are, and you want them removed, you have to let me know, and I will do that at the end of class today. If you join a wrong group, then let me know afterwards, and then I'll help you out. You can't leave it on your own. I have to remove you, Kim. Okay, so that is assignment 2. Any questions other than, I don't know, I want to leave this group for assignment 2. We have a lot of stuff to cover, guys. I have 83 slides today to cover with you and not a lot of time. And I want to make sure that you guys have enough time to go through everything. And I'm going to skip some of them. Some of them are for you to read. I'm just letting you know about this. I'm not going to read all the slides, but I want to talk about the concepts here today. And so you have enough to do your assignment number 2 and so on. All right, let's get moving. So laws of motion, what are they? It's basically what they are is the description of an object in motion, including its position, velocity, and acceleration. We've been talking about motion in one direction, motion in two directions, for the last couple of weeks and so on. We've also talked about a bit about geometry in week 1 and trigonometry. And now we're talking about 2 factors that address, what influences motion, which are force, acting on an object, and the mass of the object itself. That's the stuff we're going to be talking about. There is a famous physicist, Isaac Newton, and if you haven't heard of him, that's okay. He was alive between 1642 and 1727, formulated basic laws of mechanics, and he discovered, and we'll say discovered, the law of universal gravitation in terms of how things work, invented a form of calculus, which is awesome, and he made many, many observations dealing with light and optics and other stuff. Most of our physics we use in games are Newtonian physics, right? Because we don't use quantum physics. We don't use other kinds of physics. Usually it's just Newtonian that we use. Let's talk about force. Force is something we experience every day. When we push an object, when we pull an object, when we throw or kick a ball, all those kind of things is what we experience. And forces are what causes a change in velocity of an object. Okay, so if there's no change in velocity of an object, remember, a velocity means that there's displacement. Okay, it's not just distance. Then there's no force, no displacement, no force. Right, that's the most important thing because it's velocity, it's a vector. So that's Newton's definition. A force is that which causes an acceleration. So acceleration and force are related. They're directly proportional. Newton has, there's different kinds of forces. Let's talk about some different forces. One of them is contact forces. Things like a pulling or a spring, a kicking, and those kind of things. There's also field forces like gravity or magnetism. Those things we're not going to be dealing with too much. Gravity we're going to use, but field forces in terms of magnetism and other kinds of fields, electromagnetic fields and so on, we're not dealing with in this course, but I'm mentioning what they are. There's also electromagnetic forces, nuclear forces, weak forces. Again, these are all types of field forces, and we only care about gravitational force with respect to acceleration for our problems. Okay, we don't care about the other stuff. Not that they're not important in real life if you're a physicist, but for us, we're kind of like a micro or microcosm of physics that we're using in games. All right, let's talk about some other forces. One thing that we want to be able to do is, I'm just going to skip this slide, is talk about the vector nature of forces, all right? How forces usually are applied perpendicularly to each other. And the resultant or net force is the hypotenuse. And if you think about that, now we go back to Pythagorean theorem again, the triangle stuff that we talked about day 1 when we were together. That's why triangles are so important in game development, because triangles help us with vectors. Triangles help us with net forces. Triangles, when it comes to the components of a triangle, the x and y axis, we can decouple those components and figure out the forces, the energy that's going into one axis or another. All right, so that is the nature of forces that are vector-like. When it comes to force itself, if I want to think about this, what I'm showing here, we can see that the downward force, if I have some kind of spring, okay, that I want to measure the downward force, things that I pull down So I have an arrow that goes down. You can see that there's a force vector that goes in the downward direction, right? You can see that the second force vector here elongates the spring even more, so it provides more tension on the spring, so it creates more force as we're pulling down. We also have to think about that we might have two forces pulling in the same direction. For example, the force of gravity, and also if I'm pulling something down, as an example, we have to also consider that as well. So those two things are important. We can also have forces that push in different directions. A force, for example, F2 that's pushing across the x-axis, another one, F1, that's pushing across the y-axis. And now you can see that we have a resultant force vector with an angle and a magnitude that's pulling the spring in a certain direction. Okay, so that's kind of important information about how forces kind of work. Let's talk about Newton's laws. We're going to talk about, these three laws of physics that he talks about, that he uses basically theoretically for all of his formula, and everything else that we deal with in game physics actually is based on Newton's laws. All right. Here's one. If an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. Wow. This is also called the law of inertia. And you can also reword this thing to say something like an object at rest tends to stay at rest. An object in motion tends to stay in motion. Okay? That's the kind of shortcut to what Newton's first law is. An object at rest tends to stay at rest. An object in motion tends to stay in motion. Okay? Newton's first law. And inertial frames, what are those? We can think about a frame of reference as an example that moves with a constant velocity relative to the initial frame. And if we accelerate, relative to another object in the inertial frame, you're actually observing the form of non-inertial frame of reference. Again, the way to think about this is what an inertial frame is. Think about it as if I'm observing something that's happening, where there's motion happening, if I'm the observer from outside. We talked briefly about frame of reference last day. The difference between experiencing the acceleration and actually observing the acceleration, two different things. So Newton's first law, the alternate statement is, we want to think about something that describes what happens in the absence of force, right? So it does not describe zero net force at all. And it also tells us that when no force acts on an object, the acceleration of the object must be zero. No force, no acceleration, right? And so again, an object at rest tends to stay at rest. An object in motion tends to stay in motion. And here it is, the definition of force as that which causes a change in the motion of an object. Okay, so if there's no motion, there's no force. Okay, so that's kind of an important thing. There's also a relationship between inertia and mass. In fact, a lot of times we say that mass and inertia are the same thing. The tendency of an object to resist any attempt to change its velocity is called inertia. All right, so if I talk about the inertia of an object, it's like how much does the object resist my attempts to move it? A lot of times it's related to mass. On Earth, the more massive an object is, or more particles, more molecules that make up an object, the denser an object is, as an example, the more difficult it is to move. Or if you think about it, the ability, there's an increase in the ability for it to resist motion, or it has a greater amount of inertia, right? So masses can be defined in the terms of accelerations produced by a given force acting on them. We can say that m1 over m2 is equal to a2 over a1, okay? Approximately equal to, and the magnitude of the acceleration acting on the object is usually inversely proportional to its mass. And this kind of ties us into, the second law of motion, which we're going to talk about in a second. So mass is an inherent property of all objects, right? They have a mass or they don't. Can you think about an object in real time and in the space-time continuum that has no mass? Can you think about it? Anybody that we know of? Dark matter in the space-time continuum that exists today. Can we really detect dark matter? Maybe. Anyone else have anything else other than dark matter? Zero mass. Can you think about an object or a phenomenon that has zero mass? Light. Yeah, we think that light has zero mass. Gravity, we think atoms. No, atoms have mass. But what about, there's also neutrinos. Neutrinos are objects that have zero mass, and those kind of things. So typically, protons have mass. Sound has mass, but because sound are just sound waves, right? Oxygen has mass, right? All those things have mass, because they're made up of particles. If something's made up of particles, they have mass, right? But things that we can't detect the mass of, maybe they're micro masses or whatever, or things like light, there's no mass for light. And we can't detect mass in, for example, in neutrinos and those kind of things. So even though light has photons, or we can kind of think about them as photons, they don't have any mass. And the reason why they don't have any mass is they're in line with Einsteinian physics, and this is something beyond Newton. Einstein built on Newton's physics, and he talked about how as we approach the speed of light in a vacuum, then the amount of mass that's required, that actually we dilate, we kind of go through something called time and mass dilation, where the amount of mass that we have, that we're accelerating towards the speed of light, increases to infinity. This is something that he's found that when in nature, which means that we can never approach the speed of light in a vacuum with a regular Earth ship. It's not possible. Why? Because mass increases to infinity, which means we'd have to have an infinite amount of force to push an object towards the speed of light, which means with regular physics in the regular universe, in the normal universe, we can never approach the speed of light in a vacuum. In fact, approaching even 10% of the speed of light in a vacuum for any regular masses is impossible right now for us to do. So going back to reality, let's go back to reality for a second. Mass is most objects have masses that we know of, right? The things that we're going to be dealing with in games, all of it has mass, okay? Mass is independent of the object's surroundings. Doesn't matter where you are. Mass is independent of the method used to measure it. And mass is a scalar quantity, okay? So it's not a vector in any means. And units of mass are measured for us here is in kilograms, always in kilograms. In other places, maybe they measure masses in other things, but for us as physicists, we're little microphysicists today as we're entering this part of Newtonian physics. We measure everything in kilograms and meters for distance or for length. How about mass and weight? What's the difference between mass and weight? Well, mass is the same everywhere, right? So if I take an object that I have on Earth and I bring it to the moon, right? The mass hasn't changed, but the weight, the apparent weight or the perceived weight has changed. Why? Because of the acceleration due to gravity on the different planet, right? Which let's think about, or this different planetoid, the moon, right? This different object in space or planetary object, if you will, right? So because the moon's gravity is 1/6 Earth normal, therefore something that is normally on Earth 180 pounds, as an example, would only would feel like it only weighed 30 pounds on the moon, 1/6 of Earth normal, right? So, but the mass stays the same. Remember, I want you to think about mass in your mind as a number of particles. The number of particles in a ball. If I have a, let's say, a bowling ball. If I have a bowling ball on the Earth and I take it to the moon, the number of particles don't change. The amount of molecules that make up that bowling ball, right? They don't change. It's the same amount. It's not like I'm taking parts of the bowling ball off just because I moved to the moon or into space, right? It's just that gravity gives us the perception of weight, right? So weight and mass are related, but weight really doesn't speak to mass changing, right? The mass is the same everywhere. Where mass is different, where it becomes really weird, right, with our calculations, is when we talk about rocket science. Why is rocket science difficult? And we're going to talk about this again a couple times. Rocket science is tough because the mass of an object is constantly changing. What's the mass of the object we're talking about? The rocket. Rocket fuel has mass, and it leaves the rocket. And as it leaves the rocket, it has less mass, which means we need less force to drive that rocket as it continues to move. Making those complex calculations where mass is not a constant is much more difficult than where mass is a constant. And that's why rocket science is difficult. Okay, and not just that, but other things, of course. So let's talk about Newton's second law now. So we know that mass and inertia, they kind of mean the same things in many ways. The more massive an object, the more inertia it has, right? It's directly proportional. We can also say that force is inversely proportional to the acceleration, right? So what that means is that force is the cause that changes in motion, right? Of change in motion as measured by the acceleration, right? So in other words, if there's no acceleration, take a look at this formula, there's no force. If there's no mass, there's no force, right? So, so this is an important way of looking at this, right? So force is equal to ma, right? Or in other words, this is Newton's second law. Force is equal to ma, right? In other words, force is inversely proportional to acceleration. Let's talk more about Newton's second law. So where force, the symbol force, or the sum of all forces, this sigma here is the sum of all forces, is the net force, right? And this is the vector sum of all forces acting on an object. It may also be called the total force, or resultant force, or the unbalanced force. Okay, sum usually means the total force. That's what the sigma means. So example, we can also break it down in terms of its components, x, y, and z. So for example, I might have the sum of all forces across the x-axis is equal to the mass times the acceleration across the x-axis. And the sum of all forces across the y-axis can be said that you take the mass and multiply it by the acceleration across the y-axis. If you don't have any acceleration across one of these axes, then across that axis you have zero force. Okay? Remember that mass times acceleration is not a force, right? It's just a way of figuring out what the force is. Okay? So again, when it comes to forces, the unit of measure is newtons. Oh yeah, newtons. Sometimes we also look at them as foot-pounds. That's also another way of looking at it, right? Slug-foots. But more or less, the unit of measure can also be translated from newtons to kilogram, 1 kilogram per times mass divided by, or second squared, or kilogram masses per second squared is the way you would say that. So 1 Newton is that. Or in some other places, 1 pound is equal to 1 slug foot per second squared. Or on average, 1 Newton is approximately equal to a quarter pound. So why is it that we can compare newtons to kilograms on Earth? We got to think about this as well, right? That the mass of an object is going to be influenced by gravity, right? And we're going to see that a lot. So here's some Newton's second law examples. A hockey puck having a mass of 0.3 kilograms, right, slides on a frictionless horizontal surface. We're looking at a top-down diagram here. This is the hockey puck, okay, as an example, of an ice rink. This is the ice rink, okay? So again, top-down view, right? 2 hockey sticks strike the puck simultaneously, exerting the forces on the puck. The force F1 has a magnitude of 5 newtons and is directed at theta is equal to 20 degrees, this way, right? Below the x-axis, the force F2, the other hockey stick, right, has a magnitude of 8 newtons and is in its direction is theta is equal to 60 degrees, right, above the x-axis. The question would be, determine both the magnitude and the direction of the puck's acceleration, which is what we really want to know is the resultant force vector. What is the resultant force vector from these two vectors, right? So how do we do this? The first thing we do is, again, going back to that thing we talked about last day and the day before, which is conceptualize. The acceleration of the puck will be in the same direction, all right? So that's what it's going to be. So it's going to be one direction. Categorize. Because we can determine the net force and we want an acceleration, this problem is categorized as one that may be solved using Newton's second law. Okay, this is an important thing. And then let's analyze, right? Well, we find the component of the net force acting on the puck. What is the sum of the net forces on the x-axis? We can say that F1x plus F2x is equal to, we can convert F1x, remember, from last day when we had motion in 2 directions. Anything on the x-axis, we multiply by cos theta. We have a portion of the energy that's going on the x-axis and a portion of the energy, some aspect of the energy that's going on the y-axis, right? And so that the total energy is divided across those two components, right? So what we can do is notice that if I go back to the diagram, we have two angles, 60 degrees and 20 degrees. We want to label these angles differently for our calculations. So one of the angles, the one that's relative to F1, we label as theta, and the other one we label as phi. Okay, that's just a different Greek symbol, and this is the one theta, and this is phi. Okay, as an example, just to bring you back to that. And that's just for the x-axis. So you get the sum of all forces across the x-axis. That's how you read this symbol right here, right? And this is the sum of all forces across the y-axis. So that you take F1 plus F2, and then you convert these into F1 across the y-axis and F2 across the y-axis. That's force 1 and force 2. Those components, you can break them down into sine theta and F2 sine phi, right? And then what you do is, from an acceleration perspective, we know that force is equal to mass times acceleration, right? So if we want to find acceleration, we rewrite the formula so that acceleration across the x-axis is the sum of all forces across the x-axis divided by the mass, right? And when we do that, we can start plugging in some values that we know. So when we do this, we can figure out that the acceleration across the x-axis, we plug in the values, is 5 newtons cos minus 20, that's theta, plus 8 newtons times cos 60, that's phi, right? And we divide this by 0.3 kilograms, which is the mass of the puck. We get the acceleration only across the x-axis as 29 meters per second squared. We do the same exercise for the y-axis, and we come to 17 meters per second squared. So now we have both accelerations across the x and across the y. When we want to figure out the total acceleration, right, as an example, that's the acceleration value, the magnitude of the acceleration, not the angle, right? We take the acceleration across the x-axis squared plus the acceleration across the y-axis squared and take the square root of that. That's using Pythagorean theorem. Remember, we take two components, and then we get the hypotenuse, which is the acceleration, the total acceleration, we can say, which is 34 meters per second squared. So that's the total acceleration in the direction that we're going. To figure out the direction, we take the arctangent of AY over AX. Again, this is kind of what we've done before. And that gives us an angle of 31 degrees. So the final answer is the vector would be, kind of an angle of 31 degrees from the horizontal, so a positive angle up, with an acceleration value or magnitude of 34 meters per second squared. Okay, so that's how we would find that out. Questions around this stuff. So we've taken force equals to ma and applied a problem to it. Y minus 20. Well, we've applied an axis to this, Miguel, right? And you can see that clearly this angle here is below the x-axis. If it's below the x-axis, it's a minus 20. If it's above the x-axis, it's a positive 20, positive 60 in this case. All right, so that is the first part of our talk, and that's for Newton's first and second laws. Let's get into a few things about gravitational force. So when we talk about gravitational force, we also talk about it as the force of gravity, right? And remember what the force of gravity would be. The force of gravity is the acceleration due to gravity times the mass that we're talking about, right? Force of gravity is equal to mass times gravity, the acceleration due to gravity, okay? And we usually talk about it as force of gravity is equal to mg, not ma, okay? Because acceleration is gravity in this case. That's what the force of gravity would be. A little bit more about weight. One thing is a kilogram is not a unit of weight. A kilogram is a unit of mass, right? So again, 1 kilogram is about 2.2 pounds on Earth's surface. And we also remember that gravity works best when we're close to the center of mass. When we're further out from the mass in real physics, gravity would change. It would become less and less effective. It's almost like I have a tractor beam. I want to think about this as a tractor beam on every object on the Earth. But the further out the object is, let's say, for example, the top of a mountain in real life, then the tractor beam that I would have from the center of the Earth to the top of the mountain is weaker than if it's closer to the center of the Earth, the surface of the Earth. For example, sea level would be kind of where we can probably go. Deeper into the center of the Earth, the gravity becomes stronger and stronger. That's why the pressures, not only are the pressures due to all of the oceans on top of you, but as we get closer and closer to the center of the Earth, the amount of pressure due to gravity increases and increases and increases. It's the local weight, but not universal. Yes. So weight is always something that's local to the planet or to the altitude of where you are relative to the surface of the planet. Okay. Roughly, it still equates to, in our case, 9.8 meters per second. Roughly. Okay. For us, for games, you can even use 10. It's okay, because 10 is close enough for what we need. And again, like sometimes, like I said, for a platformer, we might use 30 because it makes more sense because we want an object to fall quicker. Isn't it zero at the center of the Earth? Well, no, the gravity continues to work on the center of the Earth, right? So it keeps on holding it close to the center of the Earth. That's why the Earth is, in many ways, why we have planets shaped as spheres as opposed to shaped like cubes, right? It's constantly pulling into the center, right? So constantly. So in Newton's laws, the mass is the inertial mass and measures the resistance to change in the object's motion. So this is an important consideration, that inertia and mass mean the same thing for Newton. Okay. Let's talk about Newton's third law now. All right, and I'm going to get you guys to think about this and recite it. So I know you can check that and Google that zero at the answer. Well, again, that's what they theorize. But if you think about it, there's constant gravity all the time, right? So that's what I'm saying. For us, there's constant gravity for games. In real life, that's a whole different thing, right? Remember, we're trying to translate Newton's laws and motion in 1D and 2D to something that works in games, right? That makes sense. That's realistic. So Newton's third law, if two objects interact, the force from 1 to 2 exerted by object 1 on an object 2 is equal in magnitude and opposite in direction to the force from force 2 to 1 from exerted by object 2 on object 1. So in other words, where it says 1, 2 and 2, 1, it's not 12 and 21. It's the force from object 1 to 2, the force from object 2 to 1. So you can see that the forces are equal and opposite. Okay, so another way to think about Newton's third law is, for every action, there is an equal and opposite reaction. And we're going to use Newton's third law a lot when it comes to collision response. Collision detection is one thing, but collision response, that's Newton's third law, right? What do we do? Any action, there's an equal and opposite reaction. Okay, that's what we're going to talk about. So the three laws are, if we're going to recap, right? Bodies at rest tend to stay at rest. Bodies in motion tend to stay in motion. That's Newton's first law. Second law is force is equal to mass times acceleration, right? We can also reword that as, the force of an object is directly proportional to mass times its acceleration, or inversely proportional to its acceleration, if you want to think of it that way as well. And the third law is, for every action, there's an equal and opposite reaction. All right, so again, one of the forces is usually the action force, and the other force is the reaction force. But it doesn't matter which is considered the action and which is the reaction. You're going to have the same amount of force. Okay, and here's an example of that. The force F1 to 2 exerted by object 1 and object 2 is equal in magnitude and opposite in direction to force F2 to 1. So I've got two forces on this bigger mass, on a smaller mass, right? They're coming together, and you're going to have an equal and opposite reaction. Okay, so if I have a force coming at this way, it's going to come right back at me in many ways, right? Some force is going to be lost in the system because it's going to kind of bounce in this way. We'll talk about energy loss later on when we talk about energy of a system. Also, when we think about Newton's third law, we also have to think about normal force. For every force, there's an equal and opposite reaction. We can say that if there's a surface, then the normal force is equal to the force times the mass of the object, right? So normal force on the table, for example, with the monitor, is the reaction of the force of the monitor exerts on the table. In other words, the reason why the table is strong enough, as an example, for it to support the monitor, the mass of the monitor on the table, and we can say that the normal force is perpendicular to the surface, okay, of the object. Here's something: force of gravity is equal to the force, times the object, and as an example, times its mass, right? So we can equally say that the normal force is really equal to the force of gravity times mass, right? So GM, normal force, is equal to the force of gravity, or the acceleration due to gravity times its mass. All right, so that's interesting. And why? Because the force of gravity is pulling the monitor down, and the normal force is equal and opposite, pushing the monitor up, right? The normal force, and this is why we say Fg, the force of gravity, is equal to the force that pushes the monitor up, right, as an example. Then we can sit there and say that the normal force is equal to the force of gravity times the mass, right, which we're going to see later on. One thing we're also going to be talking about is free body diagrams. We're going to talk about this in a second. You want forces acting on a particular object, and we use the model of an object as a particle again, right? We're going to talk about that in a second. So again, the normal force and the force of gravity are the forces that act on the monitor, right? Normal force pushes up, away from the table. The force of gravity pulls it down, and those two forces cancel each other out, so the monitor doesn't move. Okay? So Neil says, so the force is the same, but how the object moves in the reaction to the collision will depend on the angle, acceleration, velocity, and mass. Yes. And also friction, which we'll talk about later. So when we talk about a free body diagram, you've been asked to do that for assignment number 2, right? The most important step to solving a lot of problems is drawing it out first. So 1, for the mass of the object, you draw a dot. Okay, that's the first thing. So this dot here represents the particle, or the mass of the object, the center of mass. And then what you would do is you draw forces acting upon the object as a vector. So example, if we're talking about the force of gravity, you would draw that force pulling down, right? Notice that I don't have to put, what the force of gravity is, which is really acceleration due to gravity times mass, right? That's what the force of gravity is, remember? The normal force then is equal to this force, equal and opposite in direction, right? Because the normal force is holding the object up. A good example of this is if an object was on the ground, the normal force would be perpendicular to the surface. So at right angles to the surface of an object, right? If the ground was, on a slope, then the normal force would be in another direction. It would be perpendicular to the slope of the object. We're going to see that in a bit. So again, the particle model is used, to represent the object as a dot in the free body diagram. And the forces that act on the object are shown as being applied to the dot. And the free body diagram helps us isolate only those forces acting on the object and eliminate anything else. Okay, so we make some assumptions. Let's make some assumptions here when we do a free body diagram. Objects can be modeled as particles. Number 1, we're only interested in the external forces acting on the object, and we can neglect reactionary forces. And we'll talk about that later. Initially, we're dealing with frictionless surfaces. When we're learning about how this works, the motion and all that stuff, we can assume that there's zero friction, zero air friction, zero surface friction. Everything is zeroed. Why? Because friction is actually a force that works against motion. All right, we'll talk about that later on. Masses of strings or ropes are negligible. All right, so if something is holding something else up, we're going to think that a rope or chain or something else like that is either included in the mass already or is negligible. We don't have to think about it as a separate item. All right, So we're simplifying the model as much as possible, right? And the force that the rope exerts is away from the object and parallel to the rope. That's important. When a rope is attached to an object, and like example, I'm pulling something, the magnitude of the force is the tension on the rope. So I can say that there's a force of tension across that rope, how much tension I'm using. And if I want to break the rope, it might have a tensile strength, how strong an object is, the rope. If I pull it with it and I exert enough force to create a tension that rises above the tensile strength of an object, the rope will snap. Okay? So that's something to note as well. By the way, it doesn't apply to ropes. It also applies to bolts and nuts that you put inside of an object. A nut and bolt, or some kind of thing that connects an object or holds an object together, we have both tensile strength and shearing force that's required to break a nut or a bolt due to the weight of an object. Okay. All right. Let's think about this. If the acceleration on the object that can be modeled as a particle is 0, the object is said to be in equilibrium. Okay. This is a key word here. The model is the particle in equilibrium model. Okay. And mathematically, the net force acting on an object that is in equilibrium is 0. Right. So again, the sum of all forces across the x-axis is 0, and also we can say that the sum of all forces in our case across the y-axis is 0. If we're dealing with the z-axis, also 0. Okay, and the sum of all forces, period, is 0. Everything is 0. That means that all forces kind of balance out if I pull things in different directions, and that's when an object is in equilibrium. Okay, here's an example of some objects in equilibrium. This object here is not falling, right? And therefore, it's in equilibrium. It's not also moving left and right. There's no force to the left and right or on the horizontal of an object, and there's no force, acting on it to move it across, the y-axis. Remember, even though there's mass, if there's no motion, then force is 0. Right? So again, sum of all forces in this diagram is 0. Why? Because the force of gravity is being countered by the tensile force that's because we're tethered to the wall or the ceiling here, right? And this tethering force, or this tension, if you will, of the chain is counteracting the force of gravity, and so we can say that the sum of all force across the y-axis is 0, and so therefore this object with respect to y is in equilibrium. Because it's not moving back and forth, right? Across the x-axis, we can also say that there's no forces being applied to it on the x-axis, and therefore on the x-axis, the sum of all forces is also 0. So we can say that this object, this lamp, is in equilibrium. Okay, so again, if an object that can be modeled as a particle experiences an acceleration, there must be non-zero force. If I have an acceleration, we must have force in an object, right? And the first thing we do is draw a free body diagram, and we start applying Newton's second law in component form. We break down the second law, and we break it down across the x-axis and across the y-axis in order for us to, apply, the forces, the resultant force vector on it. Here's an example. So again, example 1, forces acting on a crate. The tension acting through the rope, right, is the magnitude of force T. Tension force, tensile force. The gravitational force, Fg, is acting on the crate, and the normal force, N, is exerted by the floor. We can draw the free body diagram that looks like this, where the force of gravity is being countered by the normal force. So they're on the y-axis. We can say that the sum of all force across the y-axis is 0, right? However, we do have a tension force exerted by the rope, and it's going across the x-axis. So we can say that there is a force across the x-axis to the right, or a positive force in the right direction, or positive x. Makes sense? This is the free body diagram. Again, there's some stuff missing here. We don't know what the mass is, so we can't really calculate the force of gravity or the normal force. And we know there's some kind of force happening, but we can't calculate the acceleration, right? Because we don't have the mass. So again, we applied Newton's second law in component form. We know that the sum of all force across the x-axis is the tensile force, which is equal to the mass times the acceleration across the x-axis. Again, no acceleration, no force, right? The sum of all force across the y-axis, though, as we said, is the normal force minus the force of gravity, which is 0. That means that the normal force is equal to the force of gravity. So therefore, we know that the sum of all forces across the y-axis is just 0. If the tension is constant, then the acceleration is constant, and the kinematic equations, we can start using them to more fully describe the motion in the crate, right? Okay, here's the second one. The normal force is not always equal to the gravitational force of the object. For example, in this case, the sum of all forces on the y-axis is equal to the normal force minus the force of gravity minus F, which is 0. In other words, I'm pushing down on this thing and there's a force of gravity. So now the normal force is actually not just the force of gravity, but also my additional force if I'm pushing down on the physics book. Here I have a surface and I can't break through the surface with my force from my hand, right? And so we can say that the resultant normal force, because remember, for every action, there's an equal and opposite reaction, is the force of gravity is equal to the force of gravity plus the force that I'm exerting on the book as I'm pressing down on it. Okay, just a note. So some problem solving hints like normal when applying Newton's laws. 1, draw a diagram. We said this last time too. Choose a convenient coordinate system for the model. Apply the coordinate system where it makes sense. Categorize, start breaking things out, try and figure out if there's equilibrium. Is the model a particle under a net force? If so, then if there's motion, if there's acceleration, there's a force. If there's no motion, then we can say that the object is in equilibrium. Analyze, draw free body diagrams for each object in the system, all right? Include any forces acting on the object. Find components along the coordinate axis that you've applied. You put the coordinate axis in there. And be sure the units are consistent. We usually use kilograms and meters for everything, as an example. All right. Here's another equilibrium example. By the way, these examples you're seeing here are going to be eerily similar to what you're going to get on your test, which is happening in week 7. Here's something. A traffic light weighing 122 newtons. Notice the words, weighing and newtons, right? Hangs from a cable tied to 2 other cables fastened to a support. Okay, so first of all, let's think about this, what this means. Weighing 122 newtons. Why can we say this? Because the force, we're getting a force here, newtons, right? We know that it's equal to mass times acceleration. That's what force is. But we know when we talk about weight, we're talking about gravity. Gravity is 9.8 meters per second. If we have 122 newtons, we can figure out the mass when we rearrange the equation. We know that what the two of the variables are, we can figure out the third. Okay. The upper cables make angles of theta 1 is equal to 37 degrees and theta 2 is equal to 53 degrees. We know what this angle would be, right? Because the internal angles of a triangle always equate to 180 degrees. So we know we can figure out this angle here if we need to. Okay? One thing we cannot use in this case is Pythagorean theorem. Why? Because this may not be a right angle, right? And chances are it's not. If you add up these two things, 37 and 53, what's remaining, right? That's 87. In this case, it's 90. So we can adjust for a thing, but typically it's not. This is just one case. But don't expect that this is always 90 degrees because what students do sometimes is they expect that it's a right angle, a 90-degree angle, and they apply Newton's laws. And you can't apply, they apply Pythagorean theorem. You cannot apply Pythagorean theorem on a triangle that's not right angled. You have to make other adjustments. You have to split the triangle in half and so on, and do a bunch of other stuff. Okay, so one thing to note is these upper cables are not as strong as the vertical cable, this one here, right? And will break if the tension in them exceeds 100 newtons. Okay? So we give in information about everything. Now, here's the question. This is what they're asking you. Physics question. Does the traffic light remain hanging in this situation, or will one of the cables break? We know some stuff. We need to apply it to the diagram. Let's start doing that. So we know that this is 37 degrees. We know this is 53 degrees, right? We start conceptualizing by drawing this as a free body diagram. Notice that there's a point here. This is the point of mass, right? If nothing is moving, and nothing is moving right now, we can assume that the entire diagram is in equilibrium. Okay, we make some assumptions. And we can start drawing the free body diagram. Look at what they've done. What they've done is they've drawn the free body diagram and they've applied the X and Y axis in a specific spot, right across the point of axis. How can you do this when we don't have that information here? Take a look. 37 is up here and 53 is up here. But when we draw the diagram, 53 is down here and 37 is over here. Does that make sense? And how can that be? Does anyone know? Can anyone remember? This is like triangle stuff from day one. Come on, guys. Remember when we draw a triangle, right? There's something called complementary angles, right? It's not just a 3, 4, 5 triangle. It's complementary angles. So if I was going to draw or annotate this, the triangle, right? So again, if you draw the top of this thing, right? And then you draw the diagram. So this is the diagram. You see kind of something that looks like this. And then you put your axes. Let's use another color. So this is the diagram that we were given, right? And now we want to conveniently put our axes where I want to. So now let's draw in another color here. Let's draw in a, I don't know, red color, right? So if I draw in a red color and I say that, okay, this is the y-axis here, and this is the x-axis here, right? You can see now that I have this situation, right? Where this angle up here, right? So this angle up here is equal to this angle down here. These are complementary angles. So if this is 37 degrees, so is this one. And that's why 37 is over here, right? So the angle is actually, if this is the top, this is 37 degrees up here, but so is this one. And if this is 53 degrees up here, well, the complementary angle, so is this one. And that's how you can redraw the diagram that looks like this, okay? So that's the first thing you have to do. All right, so now that we've done that and we've redrawn everything, so we put an X and Y axis across this, now we can start thinking about these as two different triangles, right? We have a triangle over here, we have a triangle over here, right? We have a force, a magnitude, and we have a magnitude on this side. We don't know what those are yet. And we do know that there is an angle here and an angle here, okay? We know that the resultant tension, which is this tension here, T3, this tension, right? We know that T3 is equal and opposite to Fg because there's no motion. We know, we can assume that T3 is in equilibrium. All right, so the tension 3 is equal to, for many ways, Fg, okay, force of gravity. Let's start breaking down the stuff that we know. We're going to say that the sum of all forces across the y-axis is 0 because T3, the tension on that wire 3, minus the force of gravity is 0, right? Therefore, we can say that T3 is equal to the force of gravity if we just move force of gravity on the other side, right? Now, this is where people get lost. I want to start thinking about tension 1 and tension 2, the force of tension on 1, the force and tension on cable 2. And how do we figure this out? Well, we know that there's two components, the X component and the Y component. And we also know that when we talk anything to the left of the knot, which is our part of our free body diagram, the dot here, this is negative. And anything on this side is positive. So X-axes on this side, right, are negative. So that's why it's written here as T1, the X component is a negative T1 cos theta 1, And the y component is a T1 sine theta, positive. Why? Because we also see in this diagram that y for both sides is up in the upwards direction. Okay, this is important to note. So that's the first thing. So we break these things down. T2 is T2 cos theta 2 and T2 sine theta 2. That's how you break down the forces of tension. And the force across the x component for T3 is 0. And we know, this is where people get confused, that the force across the y component for T3 is minus Fg. Minus Fg because when we look at this thing, T3 is in a downward direction, and so, or you can also flip it around and say that T3 counteracts the force of gravity, which means that T3 is the force of gravity, therefore it's pointing down. Okay. Then what you want to do is you want to get the sum of all forces across the x-axis and the sum of all forces across the y-axis, and you kind of put everything in one equation. You can say that the sum of all forces across the x-axis minus T1 cos theta 1 plus T2 cos theta 2 is in equilibrium. We can also say that sum of all forces of the y-axis also in equilibrium, right? So we put all those things down and we add them all up. Once we have the equations in this form, then we can start plugging in some values, right? So now we can start solving, and we want to solve for one of the terms. It doesn't matter which one, right? Where we say we solve for T2. We can rearrange the equations that we have here, and let's say, for example, I want to solve for T2. Then what I want to do is I want to move T1 negative T1 cos theta to the other side of the equal sign. So this becomes a positive T1 cos theta 1 on this side. And because we have a cos theta 2 that's multiplied by T2 on this side, if we want to isolate T2, we need to divide both sides by cos theta 2, which means here it would be T2 is equal to T1 times cos theta 1 over cos theta 2, right? So that is what T2 is. And then what we do is we take T2 and we want to substitute it into equation 2, because equation 2, that means if I took T2 in terms of T1 and put it in here, we would eliminate one of the variables, right? If I made T2, if we say T2 then is equal to T1 cos theta 1 over cos theta 2, we can replace T2, this term here, with T1 times cos theta 1 over cos theta 2. Okay, that's what we're doing here. Once we substitute that in, now we can use trig equations, trig identities to figure stuff out. Look, cos theta 1 times sine theta 2, right? If we really want to. And this is the new equation. Okay, now we want to solve for one of those things. We want to solve for the other term, T1, right? So we can say that T1, once we move these things around, is equal to the force of gravity over sine theta 1 plus cos theta 1 times tan theta 2, because once we start moving things around, we can multiply sine, or take sine over cosine. Here's sine theta over cos theta, which is just tan theta, right? As an example, and we get this new equation here. Once we've done that, we sub in the values that we know. Force of gravity is equal to 122 newtons. Sine 37, that's theta 1, plus cos of 37 plus tan of 53 works out that the tension on cable 1 is 73.4 newtons. Again, that's less than 100 newtons, so far we're good to go, right? And then once we've got things in terms of T1, we know that 73.4 is T1. We can go back here and figure out T2, because I can take 73.4, sub it in for T1 over here, multiply it by cos theta 1 and cos theta 2, and we get that the final force on T2 is 97.4, which is just under 100 newtons, which means that nothing is going to break. We're good to go. Why? Because the total tension on each cable cannot exceed 100 newtons, as was stated in the problem originally. Okay, so that's, I know, a bit of involved work, but you can see how this is broken out. And it's important to understand how we broke out and solved this problem, because this is one of the problems, almost identically, that you're going to see on your test with different numbers. All right, how about inclined plane? So that was the first thing. First thing is like the tension across two cables. You're going to see a lot of examples of this, which is these are classic problems you're going to see, okay? How about this? I have an inclined plane. So what is an inclined plane? We'll talk about this, but forces acting on the object, the normal force acts perpendicular to the surface of the plane. That's the first thing, right? And the gravitational force acts straight down. So this is where because of these two things, because we have an inclined plane and the surface of the object is on an angle, now we have some different things happening. Remember I said that x for the most part is aligned with cos, and sine for the most part is aligned with x is cos and y is sine. Typically we align both those two things, right? How many questions on the test? I will go over that later. So think about this. Here's a runaway car example. A car of a mass m is on an icy driveway, so zero friction, at an angle theta, some angle theta, okay? Find the acceleration of the car assuming the driveway is frictionless. Okay, so take a look what's happened here. One thing we do is we want to apply a coordinate system to this thing altogether, right? Notice when we start applying a coordinate system, I'm just going to zoom in here. Oops. I'm just going to zoom in here so you can see what I'm talking about, right? So as we zoom in, when we're trying to figure out the free body diagram, notice that, right, instead of putting our x and y coordinates kind of in the same way we do it, we actually put them at the angle of the slope. So x, we align our x coordinate, our x-axis along the slope. This is to make things simpler, believe it or not, okay? And then we put our y perpendicular to the angle of the actual surface itself. So y then becomes the normal, okay? Actually, it's really interesting. Y normal is exactly like this. It works like that in other problems, for example, in graphics as well, right? The normal is always perpendicular to the surface, okay? Now, here's something. The force of gravity, though, is not 100% counteracting the normal force of the object. Why? Because the force of gravity is acting straight down, but the normal force is acting at an angle. That's why there's acceleration, because the resultant vector, right, as an example, is not just straight down, but there's a bit of resultant vector on the right that's not resolved, right? So example, mg cos theta, this is where the angles are different, right? Even though this is y with respect to y, but because we put our coordinate system on an angle like this, instead of y being with respect to sine, now y has flipped and it's with respect to cos. So we can say that the normal force that's counteracting, that's one component of the gravity, right? Because we're taking the gravity and we're splitting it into components. Across the x-axis now, we can say that the component for the x-axis is mg sine theta. And across the y-axis here that we've drawn, the component of gravity is mg cos theta, right? And this is where it's flipped, okay? And this is the only time you're going to see this thing happening if we decide to put our coordinate system like this relative to the slope. Okay. I'm pointing this out there to you because some people get confused by that. I'm pointing it out because that's a solution. So again, conceptualize. We start thinking about drawing a free body diagram. And what we want to do is we want to align our axis, one of the axes, so it's perpendicular to the slope, and the other axis, which is parallel to the slope. And the parallel axis in this case is the x-axis. And what we want to do is we want to componentize or kind of decouple the component of the x component of gravity and the y component of gravity. And so we have is the y component and the normal force are in equilibrium. That means they cancel each other out. What's left is the x component of gravity, and that's what the acceleration is going to be, right? Because we have the mass, whatever the mass is, we're going to take the gravity, the force of gravity times, or the acceleration due to gravity times the sine theta, whatever the angle is, and that is going to be our resultant force. Okay. So knowing that, we can start plugging stuff in. We can say that the sum of all forces across the x-axis is equal to mg sine theta, which is, we break it down into the mass times acceleration across the x-axis. That's what really this mg sine theta is. F is always equal to ma, right? And the sum of all force across the y-axis is the normal force minus mg cos theta, which is equal to 0. Therefore, we only care about the acceleration across the x-axis, which is g sine theta, right? G sine theta. Why? We have canceled out the mass on both sides. So mass is inconsequential. We don't care. Mass is actually canceled out, right? Mass is not important here. What we know is that the acceleration across the x-axis is equal to the gravity, the acceleration of gravity times sine theta, right? And that's how we can get the acceleration across the x-axis. Then when we sub in our numbers, we can figure out the answer. All right. So that is another type of the inclined plane solution. Next one. Okay. And again, I'm rushing because it's 12:19 and I have still 30 slides to go. One block pushes another block problem. Okay. So two blocks of mass M1 and M2 respectively, where M1 being greater than M2 are placed in contact with each other like this, right? They're on a frictionless horizontal surface, right? As in A. Constant horizontal force F is applied to M1, right? Find the magnitude of the acceleration of the system. Well, this is interesting. So I have two masses, mass 1 and mass 2. What are we going to do? If you think about it, we're going to think about this whole mass 1 and mass 2, as a total mass. We're going to add them together. Right, typically is what we normally would do, right? Because I'm pushing both masses on a frictionless surface. It's like I'm thinking about these both masses as one big mass. So here we can start drawing our diagrams, right, as an example, right? And there's some things that we need to know. We know that for every action, there's an equal and opposite reaction. If I push M1 against M2, we're going to get something pushing us back. Remember, the inertia of the system is something that's going to resist, okay? And we can start breaking this stuff down. We can say that the sum of all forces across the x-axis is equal to the total force, which is equal to m1 plus m2 times the acceleration across the x-axis. We can say that then the acceleration across the x-axis is equal to the force divided by m1 plus m2. Notice that we're adding up those two masses as if they're only one big mass. Okay. When two or more objects are connected or in contact, Newton's laws may be applied to the system as a whole. All right, so this is important. The system as a whole, or to each other individual object. It's up to you. Whichever you choose to solve the problem, the other approach can be used to check. Okay, so it doesn't matter if you do it separately or if you do it together. The system as a whole thing, I think, works a lot easier for us as game developers. Because, thinking about two masses that are in contact, now you're just adding the two masses together, and that's the inertia of the system. That's how much masses are resisting me when I'm pushing against them, okay? All right. So one thing that we're also going to see is this kind of thing, where we have a pulley, okay, or Atwood's machine. Guys, pulleys for us in game dev, very rare. I'm not going to, whenever we see things like this, I'm not going to push you, to figure this out. Okay, I'm not going to push you to figure out pulleys. Whenever we see pulleys, I'm presenting them to you because it's a problem. But you're not going to see a pulley on a test or on an assignment, ever. Not for me. This is kind of more advanced. There's a lot more to do with this one, and it can be quite complicated. And a lot of times when we do something like this in game dev, we don't use this kind of thing very often. Okay, just letting you know. Well, it's a blessing because it doesn't make sense. So I can present Atwood's machine, but at the end of the day, Samuel, it doesn't make sense for us, right, as game devs. Just like calculus doesn't really make sense for us, right? Although it makes sense for physicists. All right, here is another one, another pulley example, where we have a mass and we're on a pulley, and then we can try and figure out the acceleration of the mass. Again, you see something like this, we're not going to present it. but this is another multiple objects with a chord and a tension and acceleration. We can draw free body diagrams because this is on a slope, so it's on an incline. You won't see a question like this. Okay, let's talk about forces of friction. And now we're getting into friction. So far, up until now, for the first 60 slides, right, we said there's zero friction. Okay, we don't care about friction. But now we're going to start talking about friction. So when an object is in motion on a surface or through a viscous medium, by the way, a viscous medium is also the air. We want to think about the air in terms of, instead of oxygen, it's oxygen, nitrogen, and other things. And really, if we think about the air as a fluid, not necessarily as a gas, right? Then when we move through the air, particles surround us and create friction. They push against us because air particles, right? There's particles in the air. There's mass that's floating around, right? Even though it's small amounts. But when we're going fast, if we're moving quickly, those particles press against us to cause heat. And it's because of the friction. We have a friction or a resistance, if you will, to motion. And that's exactly what it says here. The resistance, when it comes to moving, is all around. It's called the force of friction. So if I have some kind of resistance to motion, that's what we're talking about. And this is due to the interaction between the object and its environment. Okay? So when we think about the force of friction, how do we figure this out? Luckily, we have something called the coefficient of friction with respect to different kinds of objects. Okay, so we can say that the force of friction, or Fs, is less than or equal to the coefficient of friction, right? And there's different kinds of friction, right? We're going to talk about Fs being static friction, right? And times the normal force. So we can also say that the force of kinetic friction, right, or dynamic friction, if you will, is equal to the coefficient of kinetic friction times the normal force. All right, so usually if you look at this, remember the normal force is mg, mass times gravity, right? So we already have an idea of how much the force can be. Why? Because we have mass times gravity. Mass times gravity is like ma, right? And all we need to do is multiply it by the coefficient of friction, whatever it is, whether it's kinetic or static, and we multiply it by that amount to get the total friction force, right? For different types of frictions. So again, for static friction, this equals to how much force it takes for me to start motion. That's the force of static friction, okay? So, and the force of kinetic friction is the force of friction that's acting upon me while I'm moving. Okay, so different kinds of friction. So coefficient of friction really depends on the surface and the contact. Static friction is generally greater than the force of kinetic friction. A good example of that is if I'm trying to push an object that's at rest. Remember Newton's first law? An object at rest tends to stay at rest, which means it's going to be a greater resistance for me to get that object moving. But once it's moving, there's still going to be a bit of resistance as I go through the entire, the motion. Okay. Actually, it could be a lot of friction depending on the surface. The direction of the frictional force is opposite to the direction of the motion and parallel to the surfaces in contact, which is kind of important to note. So let's take a look at some examples, right? Static friction acts to keep the object from moving. So we take the inertia of the object, inertia being mass times gravity, and we multiply it by the coefficient of static friction, ms or mu s. I said m, but because in my mind, I'm Greek, I think mu is m. And in fact, we say mu in physics, but I say mu because in Greek it's mu, not mu. All right. But in physics, when we talk about physics for games, it's mu. So the coefficient of static friction is named as mu s, where s is static and mu is the coefficient itself, right? So that's the coefficient of static friction times the force, the normal force, right? And we can say that the normal force is mg, so mass times gravity, right? So the more massive an object is, we can say that there's more force that's required for the for us to overcome the force of static friction, right? Why? Because the static friction pushes against our force. So notice the force, in this case, we're trying to move it to the right. but the force of static friction is acting against us by pushing against the object or resisting us in the opposite direction. Okay. If the amount of force that we're applying to an object, exceeds the amount of static force, right? Static friction, then we have motion. So we could have an if statement for going from static to kinetic. You could, for example, if I start moving it, I've overcome the static friction, and now I'm applying kinetic friction for every frame after that, right? Because I'm already moving. And for kinetic friction, it's acting on an object when an object is in motion, right? So as I'm moving, then the force of kinetic friction is moving against me to slow me down. If I don't continue to apply force, as an example, if it was if the force initially was from something like gravity, that loot box that we talked about earlier, I said something like, it's right here. It says, we have a loot box, as a loot crate at the top of the frictionless ramp. I know some people, they get triggered by when I say loot box or loot crate, right? But at the top of the frictionless ramp, it falls down, but then it hits the bottom, and the bottom has force, right? And I give you the force. So I say if the coefficient of kinetic friction is 0.42, why didn't I give you the coefficient of static friction? It's already in motion, right? So I've given you this coefficient of kinetic friction. Calculate the new net force and acceleration. Okay, so think about that acceleration being negative because I'm slowly to slow things down over time. Okay. So going back to this, that's what the difference between kinetic friction is and static friction. Static friction stops us from moving. Kinetic friction is applied while we're moving. Okay. So going back to this, we can vary the applied force, right? And we can compare the values, right? Again, take a look at the static region. So the static region is this region where we start applying, static force first. And as soon as we supersede or exceed the amount of force required to start moving the object, then we move into the kinetic region where I start. And this is just like what Neil said, we can kind of say if, our applied force is greater than the force of static friction across the x-axis, then we can start moving. And now we're applying kinetic friction to this force every frame, which means we'll start moving, but we won't move fully as fast as we would do on a frictionless surface. We're going to move slower. All right, let's take a look at some popular coefficients of friction. Rubber on concrete. Guys, of course this makes sense, right? Where it's the most difficult thing. If I put rubber on concrete, that's why the coefficient of static friction is 1. So if I want to stop something from moving around and I want to have the full normal force applied, right? The full normal force applied, I use rubber on concrete. If I'm using steel on steel, that can be a little bit, as an example, some motion. There could be some motion here, right? As an example. A car tire is a good example of that, where the reason why we use car tires is because the car tires push away from the surface of the earth or the place that they're moving. That's how tires work. That's how the wheel works. It pushes away from the surface as we're moving forward. Okay. If rubber on concrete, while we're moving, you can see that is 0.8. There's still quite some resistance. All right. Rubber on concrete. Steel on steel, it goes down. In our example, we said steel on steel was 0.4. It really depends on the type of steel. Aluminum on steel, you can see is less, right? It's kind of more slidey. Glass on glass, again, you can see that there's quite a bit of static friction on glass, but when we're moving, it's good. And you can see that if you ever try that out, take 2 panes of glass and move them across each other, it's hard to get it going, but once it's going, it's much easier, right? And that's how it works with glass on glass and so on, other things. Ice on ice, look at that one. That's an important one, which is 0.1, right, and 0.03. And joints in humans, like, for example, things like our knee joints and elbow joints and, things like neck joints and shoulder joints and all that kind of stuff. All this stuff has a bit of static friction, right? But then as we're moving, once we start moving, it's not that bad, right? And the reason why this is important to note is that's why people have, over time, the more mass they have, the more damage they cause to things like limbs, hips, joints, elbows, whatever you want to call it, because there's a lot of mass and there's still a little bit of friction. It's not zero, it's not frictionless, right? And that's why they always say keep lean, and then you'll have less problems with your joints later on in life. Okay, let's continue. Let's think about friction and Newton's laws problems. Friction is a force, so simply it's included in the sum of all forces calculations. All right, that's important. The rules of friction allow you to determine the direction and magnitude of the force, right? As in positive or negative, right? Because friction always works against, the force that we're using to apply to an object, right? So it's usually negative. So here's an example of that. Suppose a block is placed on a rough surface inclined relative to the horizontal as this. Again, we apply the same thing as an inclined plane. This is something you may get, and you just saw it. I just presented this to you as one kind of a problem in your assignment 2, except there is no force here. There's a force down here, force of friction down over here when we draw it, right? So the incline angle is increased until the block starts to move. So how much do I want to, what's the correct incline angle, right, for the block to start to move, right? Because you need more of an incline angle, which means we need to have an angle, mg sine theta has to be greater than the force of static friction. Does that make sense? Because mg sine theta, as the angle increases, so too does the force across the x-axis that's going to overcome the force of static friction for the block, and eventually it's going to start moving or roll over, which is more common if you try and do a physics simulation. So that's what happens there. And when we conceptualize, I'm just going to skip these parts, then you can see that the sum of all forces across the x-axis is mg sine theta minus the force of static friction, which is 0. And then when you move things around in equation 3, we can say the force of static friction is equal to mg sine theta. When you rearrange those, it becomes n tan theta, right? Force of static friction is the normal force tan theta, tangent. And then we can figure out that what's going to happen when we start figuring out what that is based on these same equations. If I move forward, let's just move to a friction example number 2. Now the puck we're looking at it from the side view, a side split of what the puck would look like. We're not top down anymore, right? Hockey puck on a frozen pond is given an initial speed of 20 meters per second. Okay, so that we have motion already. If the puck always remains on the ice and slides 115 meters before coming to rest, determine the coefficient of kinetic friction between the puck and the ice. So how much am I slowing down every frame is what this is basically saying, right? Because we're going to get slowdown. Ice is not a perfectly, frictionless surface. There is a little bit of friction. If you look back at those coefficients for a second, right, you can see that ice on ice, you get 0.03. The coefficient of kinetic friction is low, but it's still there. That means there is a bit of a slowdown. And that makes sense because if I hit, kind of a slap a puck across the ice with my stick, right, at the example, right, then it's going to go for a while, but eventually it's going to stop. It's not going to go forever. Nothing is, infinite, right? Samuel says, it depends on how much hockey player blood there is in the way. Okay, there you go. That's pretty funny. All right, so that's the problem. How do we break this problem down? Again, we conceptualize and we start working out the problem where we have the mass times gravity is equal to the normal force. That's in equilibrium. So now we have to see how much motion there is that's going to be counteracted by the force of kinetic friction. We know some things. We can start putting things in equations. We can say that the sum of all forces across the x-axis is equal to a negative Fk, right? Because, which is equal to the mass times acceleration across the x-axis. The negative Fk force of kinetic friction is a negative sign because it's pushing against the, the acceleration. Okay, that's important to note. Whereas the sum of all forces across the y-axis is 0 because there's no motion on the vertical. It's not going up and down. The puck's not flying up and down. It's just staying across the surface. Therefore, all we really care about is the force of kinetic friction, which can be translated into a negative coefficient of kinetic friction times the normal force, right? And that's what this side would be, which is, again, equal to, if you really translate this, normal force is equal to mg. So that we can rewrite this as negative mu k, which is the coefficient of kinetic friction, times mg, which is equal to max. We can sub out the mass. We don't care about the mass of the object. Who cares, right? Because mass is moot, if we will. All we care about is that negative mu k times g is equal to the acceleration across the x-axis. So ax, or the acceleration across the x-axis, is equal to negative mu k times g, which is the coefficient of kinetic friction times gravity. That's all we care about. Everything else has been canceled out, right? And when we work this out as an example, then we can say that once we figure this out, apply the particle under constant acceleration model to the puck, right? Which is, if you think about this, vxi squared plus 2axf, right? Remember, x final this is our kinematic equation, right? Across this object, we're going to sub in for acceleration ax negative mu kg, and that's why the formula changes, right? As an example, to the velocity across the x initial squared minus 2 times mu kg x final, right, is the formula. And we get these from our kinematic equations from last day, okay? And then finally, I know I'm timing out, guys, bear with me. Mu k, we can say, is equal to the velocity across the x-axis initial squared over 2 times gravity times the the total distance final, right? And we can say then that mu k, when we sub in the numbers, 20 meters per second, which is the velocity initial, squared, over 2 times gravity, 9.8 meters per second squared, times 115 meters, the final position of the puck, right, as an example, is equal to 0.177. So actually this surface kinetic friction, if you will, for this surface of the ice is 0.177. And it's going to vary again, because not all ice surfaces are the same. Maybe there's blood on it, like Samuel was saying. Whew. Makes sense? So again, we're using a kinematic equation to figure out the force of friction. All right. And again, this is another example, friction example 3. Don't worry about pulleys. If you see a pulley example here, it's for your enrichment. It's for your knowledge. It's not because I'm going to put an example like this on a test or on an assignment. It's telling you that we can also work out the same equations on, there we go, skates create a different tension. That's what this is. And I'm not going to analyze this model because it's outside of our scope. All right, here's some example questions, and this is for your homework, starting off with number 79. So there's the last few, I would say 5 slides here are example questions for you to take away, right? And we're kind of right on time here at 12:42. So number 1, 79. A woman weighs 120 pounds. Determine A, her weight in newtons, and B, her mass in kilograms. Okay, it's a pretty simple question. How do you figure out weight? And how do you figure out her mass? Right? What is weight? And I say weight in newtons. Newtons means force. Force equal to mass times acceleration, right? So they can figure out her weight in newtons, right? If I know it's 120 pounds, if that's what she weighs, that also speaks to her mass, right? Because we can figure out mass if we have her weight, right? Because this is mass is equal to weight is equal to mass times gravity, right? So in some ways we can figure this out. All right, so let's go back to the next one. A car with a mass of 850 kilograms is moving to the right with a constant speed of 1.44 meters per second. What is the total force in the car? What is the total force in the car if it is moving to the left? Right, so this is important to get yourself going, get your mind working, which is important. So how would I do this? The first thing I would do is draw a free body diagram. Where's the point? That's the car. And then I'm moving to the right. That's cool. What about my normal force and the force of gravity on the surface? They're canceled out. So all I care about is the sum of all forces across the x-axis. And we know that force is equal to ma. We've been given a constant speed, right? So how do we figure out, the force? Okay, it's not an acceleration. We've been given a constant speed. So, well, no, is it? Is it though? Right? So think about this. So let's continue. Then there is the example of this one. Okay, and I've kind of drawn this out for you to see that. So force exerted by the wind on the sails of a sailboat is 390 newtons north. Right? The water exerts a force of 180 newtons east. Right? If the boat, including its crew, has a mass of 270 kilograms, that's not too much. Small boat, right? What are the magnitude and direction of its acceleration? Well, we can easily see that it's this, whatever this is, right? So I've got this component and I've got this component. I want to find this component. That's what I'm doing here. All right, let's continue. Last couple of questions. A force F applied to an object of mass m1 produces an acceleration of 3.0 meters per second squared. Now we have acceleration. Yay. The same force is applied to a second object of mass m2, and it produces an acceleration of 1.0 meters per second squared. Okay? What is the value of the ratio between m1 over m2? What is that value? And if m1 and m2 are combined into one object, find its acceleration under the same of the action of the force F. If I combine those two masses into one object, how do I figure that out? Draw free body diagrams for each situation. One for mass 1 and the other one for mass 2. Right? Remember that if I can accelerate an object, as an example, to the right, then I can figure out the force, right? Relative force, because my relative force is my acceleration times m1, right? And the same relative force is my acceleration, 1.0 meters per second, times m2. That's the force, right? And then once I take that, if I take the m1 over m2 value, how do I figure out the ratio, right? I already have a ratio. I have some numbers. But one thing I haven't been given is the mass. And is it important to know? That's the question. The last one. So here's an example of the same question I gave you earlier. Instead of it being some kind of lamp, now it's a bag of cement. Okay? But the question is identical. Guys, you're going to see questions like this, very similar to this on the test, right? A bag of cement weighing 325 newtons hangs in equilibrium from 3 wires. 2 of the wires make angles of 60 and 40 with a horizontal, right? Assume the system is in equilibrium. Find the tensions of T1, T2, and T3. There's no question as, is it going to break? What are the tensions now? I'm asking you for the tensions for each of these things. Oh no, tensions definitely on the test. This is on the test. Something like this is on the test, but no pulleys. Pulleys are not on the test. Tension and springs are also going to be on the test. That's for sure. We're going to talk about springs as well. Okay. Any other questions before we move on? This is the Newton's laws of motion, presentation. Again, thoughts for you guys. Know Newton's laws of motion from the top of your head. For an object at rest tends to stay at rest. That's where friction comes from, right? An object in motion tends to stay in motion minus the friction, right? If there's no friction, right? Force is equal to ma. That's the second law of motion. And the third law of motion is for every action, there's an equal and opposite reaction. And we're going to see that when it comes to collision response, right? And also, we also see that as in the normal force. The normal force is the equal and reaction, the equal and opposite reaction of our gravitational force. So if I have a gravitational force acting on an object on the surface, there's a normal force that's pushing up against the object to hold it on the surface, and so it doesn't sink into the surface. If the tensile strength of a surface, as an example, is compromised, right, or is weak, the object will actually penetrate the surface and fall into it. And so therefore the normal force won't be enough to press against the object to hold it on the surface. Okay, most times for us, the normal force is enough. Okay, we don't allow you to penetrate the surface of a driveway with your car. Okay, that doesn't happen typically. Okay, any questions around this, the lecture stuff? Let's also remind you of a couple things. One, your assignment 1, for all intents, for most people, is due on Friday. This Friday coming up, that's tomorrow at midnight. That's when it's due, okay? No exceptions. So don't ask me for extensions or anything else like that. We've had, a couple of weeks at least to get this started and done. It's not exceedingly difficult. Unless you have a medical reason, it's due tomorrow at midnight, okay? That's when it's due. And your other assignment, assignment 2, is due in 2 weeks from now on week 6 at midnight. Does it say Sunday? If it says Sunday, then it says Sunday. Let's take a look at that. Does it say Sunday? Friday, October 1st at midnight. What did we do here? Did we move it to Sunday? Due date is October 1st. See? Friday. Sunday, okay. Sunday is the last day you can submit with penalty. That's what it means. Okay. Any other questions? All right, so that is when this is due. And again, please make sure that you sign up for groups, A2 groups, as an example, for the second assignment. Remember that you cannot just assume, because you're in a group right now for assignment 1, that it's going to carry on into assignment 2. You need to resubscribe to or register for a new group for assignment 2. Catherine says, do we add you to our repository or Joss? Both? I'd like to keep my repository private. No problem. For assignments, you add me. Joss isn't going to mark your assignments. It's going to be me. Joss is marking your labs. Okay? I mean, if you want to add Joss, you can, but it's not required. Okay. Carl, which example problems best describe the part 1 question in assignment 2? It's a combination of things, actually, Carl. One of them is the inclined plane example, and plus friction across a flat surface. So what happens? We have 2 problems in one for assignment 2, really, if you think about this. If you draw this out, right, and I know I'm kind of going overtime, guys. I really do apologize. I'm just trying to answer some questions here so that way, everyone's happy. But the way it works is this. If you think about this physics problem, it kind of looks like this. We have some kind of incline, right? And let's suppose the incline is very long like this, and the crate is at the top of the incline. There's this part of the problem from here to here, and there's another problem from here to here, right? You can break it down into 2 separate problems, and let me just draw a different color here. So you can see that this problem here, from here to here, is a separate problem than this from here to here, right? But one problem feeds into the next problem. So there's 2 steps, if you will. The first step is this part, which is compute the free body diagram of the loop crate at time 0. What's the free body diagram of the loop crate up here? Compute the net force and the acceleration of the loop crate at time 0. Given the frictionless surface, what do we know about the acceleration as the object moves down the ramp? That means from here to here. Consider the loop crate as it leaves the ramp. Now that's a second problem, right? And it goes onto a flat surface here. That's a second problem, right? Compute the free body diagram here. And then if I've given you the coefficient of static friction in this case, right? The kind of steel that we're doing, calculate the new net force and acceleration across the x-axis. What is it, right? And if you keep going with this kind of stuff, it asks you other things. It says that, and I'll keep this diagram here, if we assume that the force of friction is constant after this point, how long, I'm asking for time, how long will it take for you to stop moving, right? And at what distance? What's the distance from here, the range, from here to here, the displacement from this point on? In meters, will the loop crate stop? How many, what's the distance here? So that's 2 problems, right, that you have to kind of break it down. All right. So that is that. Hopefully that kind of example helped to kind of break it down. Any other questions around anything we talked about today? Again, I'm recording all this, guys, so you can always go back and view this if you missed something. Um, Otherwise, I'm going to stop right now. How many questions are on the exam? I'll let you know that in a second. I'm going to stop recording now. Okay. All right.